Alright, gang, here we go. This is for Chem 2, Unit 8. We're going to be talking about solution making process today. A lot of this should be review from previous units. Maybe just a couple of new ideas just here and there, but for the most part, this shouldn't be too difficult. Alright, so solutions are homogeneous mixtures of two or more pure substances. Alright, so we've homogeneous, same throughout, okay, and they're mixtures. Alright. And so in a solution, the solute is dispersed uniformly throughout the solvent. Okay, remember the solvent is the thing doing the dissolving, and the solute is the thing being dissolved. So if you have a solution of sodium chloride in water, the solvent would be the water, and the solute would be the sodium chloride ions. Okay. All right. We classify the ability of substances to dissolve to form solutions depend on two things. All right, the natural tendency towards mixing and the intermolecular forces. All right, so this is why we're talking about this right after we talk about intermolecular forces. Okay, so natural tendency towards mixing. Essentially, when we talk about this, 90% of what this means is just gases tend to diffuse. Right? When we talked about gases laws, we talked about diffusing and effusing gases. Okay, so remember, gases tend to, like, they'll start in one place and they'll spread out. So if you're at home and your significant other or your wife or I guess that'd be the same thing, your mom or your dad or your cousin or somebody's making somebody in a kitchen, okay, and you can smell that hot dog they're making, and you'd be like, wait, I smell a hot dog. It's because the gas went from the kitchen where the hot dog is being made to your nose. Okay, and so that's the natural tendency towards mixing. That water, those molecules that made up that smell are going to travel through the gas eventually until they reach your nose, and they're going to spread out evenly throughout the room. Okay. So this mixing of the gases is a spontaneous process, and this spontaneity comes from this idea of entropy, which we might have mentioned recently or briefly. I can't quite remember if we did or not. Okay, but entropy is a measure of the disorder. Okay, and one of the laws of thermodynamics is that the universe is always going towards increasing entropy or increasing disorder. So as whatever systems increase the entropy of the universe tend to be spontaneous. Okay, so because a mixture is more disordered than a separated thing, then therefore it's going to tend towards that. So in this case here, we've got this container with oxygen on one side, argon on the other. If we remove and it's very ordered, right? All our oxygen are on the left and all the argon are on the right. If we remove this, then this is more disordered. We got argon and oxygen all mixed up in there together. So this has more entropy on the right-hand side over here. So because it has more entropy, it's a spontaneous mixing process. All right. So this is that natural tendency towards mixing, and it's really all dependent upon it's really about gases. This does happen to liquids to an extent, but intermolecular forces play a much bigger role in a mixture of liquids. So this is just a recap of the intermolecular forces we've talked about. Remember, dispersion forces occur everywhere, and remember, we can increase our dispersion forces by increasing mass, increasing surface area, shape, so on and so forth. So so dispersion forces will keep these guys together. Everything has dispersion forces. We also have dipole. This occurs between things that are polar, right? So you got acetone here, it's got a positive end and a negative end over here, and then chloroform, you've got the positive end right here with that hydrogen and the negative end with all these chlorines sticking out. And you also have hydrogen bonds. Remember, you have to have fun, F-O-R-N, attached to the hydrogen, right? And so you've got this hydrogen bond occur right here, and then you've also got an ion dipole, right, where you've got an ion and then mixing it with some solvent that has a dipole. Okay, so these are intermolecular forces, and really our strength is increasing this way. All right, so these are the weakest, and then these are the strongest. All right, so any of these intermolecular forces, we tend, when we first learn about intermolecular forces, to focus on intermolecular forces that are occurring between the same molecule. We talk about water has hydrogen bonds with itself, but remember, intermolecular forces can occur between anything that has both of those things. So notice that in all four of these cases, that it's not the same molecule. We've got acetone and chloroform, right? It's the same. So you would dissolve the chloroform in acetone probably, okay, or you would dissolve your heptane and pentane, okay, so on and so forth, or your ethanol in water. All right. So these intermolecular forces can be between the solute and the solute, the solvent and the solvent, or the solute and the solvent. So whenever you're making a solution, all right, there's three different attractions that you have to keep track of. All right, there's the solute to solute interactions. So these would be the things. So for example, we'll just talk about sodium chloride because it's a pretty easy example. Okay, the solute-solute interactions would be the sodium chloride bonding to itself. So it'd be those electrostatic bonds that are keeping those ions together. Okay, and in order to make a solution, you have to be able to break up those interactions. All right, you also have the solvent-solvent interactions. Okay, and these are between the water molecules themselves in the sodium chloride example, or whatever your solvent happens to be. All right, and then you also have to overcome that, and then finally you have the solute-solvent interactions, and this is really what brings your dissolution happening to, where your solute gets attached to your solvent, and you can actually have a solution being formed. Okay, and so here's just a way of picturing it. And again, they use sodium chloride because it's like the quintessential example of dissociation. So anyway, so you got sodium chloride here, and you got water as your solvent, sodium chloride as your solute, and the water molecules come in. Right, and we've talked about this before, and they surround these ions, and the sodium, or the chlorine, excuse me, gets surrounded by the hydrogen end of the water, and then the sodium bits, the purple ones, get surrounded by the negative end. So we get this hydrated chloride ion and this hydrated sodium ion. Okay, and so in order for this to occur, okay, these water molecules will be attracted to each other via hydrogen bonds, and these sodium and chloride ions will be attracted to each other because of electrostatic forces. Okay, so those two forces would have to be broken up and then replaced by this solvent-solute interaction of this dipole ion, or this ion-dipole interaction. Okay, and so really it all depends on the thermodynamics of it, right? Looking at the energy, right? The enthalpy changes. Okay. So here we've got energetics of solution formation. So we've got enthalpy in the y-axis and right here. So as we go up, we increase in enthalpy. So any movement upwards is an endothermic process. Energy has to come in, okay? And then any movement downwards is an exothermic process. So on the left, we have an exothermic solution process. All right, so here we have the solvent molecules. So in order to break those bonds up, or those, so not bonds, intermolecular forces up, we'd have to put energy in. Remember, you can almost think of these intermolecular forces as kind of like magnets, right? In order to break up two magnets, you have to physically put energy in to pull those magnets apart. Okay, so you put those, pull them apart, and then they get broken apart here. And so it takes energy to do that. Same thing happens with the solute. They're attracted to one another. In order to break them up, you literally have to put in energy, right? If they were magnets, you'd have to reach in and grab them and pull them apart from one another. Okay, so these two things are always an endothermic process, and we reach this top line right here, both of these guys. Now, to make whatever this specific solution is, it releases energy as these two things mix, the solute and the solvent. And notice that in this case it's an exothermic reaction, and it's always an exothermic reaction. The difference is whether or not this delta H of the mixture is a bigger change than this sum of the solvent and the solute enthalpy changes. Okay, so in this case, the delta H of the mixture is bigger, so you get an overall negative enthalpy, so it's an exothermic reaction. Okay, so you call that delta H of the solution right here, SOLN. Right, endothermic reactions work very much the same way. Notice that you got your solvent and your solute, and they add up to be this value up here, and then you've got your delta H in your mixture. It's still exothermic, but it's significantly less exothermic than these guys were endothermic. So overall, it's an endothermic process. You have this delta H, and notice that it's greater than 0 because it had to take energy in. All right, now anytime you have an exothermic solution process, it's always spontaneous. Okay, always spontaneous, because you're releasing energy to the surroundings, which increases entropy, and entropy of the universe always increases. So anytime you have an exothermic solution, they are spontaneous. All right, endothermic solution processes only occur if you can add energy to it, right? When that wouldn't be spontaneous because you'd have to put energy in. And the other way that it really occurs is if this delta H is really small. Okay, so if it's like, so this here, it's fairly big. I mean, obviously we don't have values, so we can't really tell what the difference is, but it would have to, if they're really, really close, then it kind of like, it's close enough that it can kind of occur. But those are the cases. You either have to put energy in to make it occur, or it has to be a really small endothermic reaction in order for it to occur. All right, so that's kind of the thermodynamic reasoning of why solution occur. Now, one thing you have to be careful of is just because you put a solid in a liquid and it disappeared doesn't mean that you have a solution. Okay, or that your substance dissolved or dissociated. Okay, sometimes it disappears, right, into solution because you actually had a chemical reaction. All right, so for example, here you had hydrochloric acid with nickel. All right, you put that nickel and the hydrochloric acid in this test tube is what they've done, and it looks like the nickel dissolves, but in actuality, the nickel reacts with the hydrochloric acid to form nickel chloride and hydrogen gas, and we can prove that by dissolving or releasing or evaporating all of the water. Once all the water is gone, then you're left with this new compound that is not nickel. Nickel is silver. This stuff's green. This is a nickel chloride hexahydrate. All right. Okay. The other thing that and for those of you sleuthy chemists out there, is like, well, of course it's not dissolving, because dissolving is a physical process. Okay, but this changed color, and changing color is a sign of a chemical process. Okay, so that's another hint before you even get to this step that this is probably a chemical reaction. Now, there's other examples where you have a solid and it doesn't have a color change. So that the color change isn't really a good way of making sure. The best way is to do what they've done here. Okay, put it in there, let it react or dissolve, whatever it's doing. Let the solvent evaporate. Okay, and then whatever you're left with, you can test that to see if it's the same as what you started with. All right. Now, so we talked about dissociation, okay, or dissolving. All right, so that's when your solute and your solvent combine to make your solution. You can also have it go the opposite way, where your solution breaks up again into the solute and solvent, and we call that crystallization. Okay, and these form two processes. So remember a couple of videos ago, maybe last video, I can't quite remember, we talked about vapor pressure, we talked about dynamic equilibrium, how we have evaporation and condensation, and they start happening at equal rates if you have that closed container. All right, you can have the same thing here. When your solute and solvent combine, they form a solution, right? This homogeneous mixture, but then it can separate. Your solute comes out and crystallizes. Okay, so you can reach a point where you reach dynamic equilibrium again, where the solution or the dissolving and crystallization rates are equal to each other. And once these two rates are equal to each other, okay, that means that you've reached this dynamic equilibrium and you can't dissolve any more solution or any more solute in your solvent. So we call this a saturated solution. All right. Now, the Chem 1 definition of saturated solution is essentially that you've put as much salt in or whatever in there as you possibly can. All right. But really what it has to do is it has to do with these rates, is the rate of dissolving versus crystallization. So if we haven't reached that amount yet, then we call that an unsaturated. So if the rate of dissolving is still greater than the rate of crystallization, then it's an unsaturated solution. Okay. Solubility, all right, is the maximum amount, is defined as the maximum amount of solute that can dissolve in a given amount of solvent at a given temperature. Essentially what this is telling you is at what amount added do you reach dynamic equilibrium, okay? And it all has to do with just how much you've added. The more you add, the more dissolving is going to take place, but because you've added more and it's dissolving more, that means you're going to make more of the product on the right side, which is your solution. But because you have more solution, you're going to be able to have more crystallization happening. And so your solubility is telling you, well, how much do you have to add before you reach dynamic equilibrium? All right, so when you're at your solubility level, you have your saturated solution and you have that amount of solute dissolved. Okay, when you pass, or if you haven't reached that point yet, then you're unsaturated and you have less than this amount. So it's just another way of looking at your saturated versus unsaturated. And then there's one more type of solution that's called supersaturated solution, and these guys are super interesting. In a supersaturated solution, you have the solvent holding more solute than is normally possible at that temperature. So you're past the solubility level. Okay. In order for this occur, what happens is you'll take whatever your solution is and you'll raise the temperature, and so that you increase the solubility of whatever you're talking about. Okay. So in this specific example, in order to make this solution here, the supersaturated solution of sodium acetate, they raised the temperature, dumped in a bunch of sodium acetate so it was soluble, stirred it up so it dissolved, and then let it cool very, very slowly. And because it cooled very slowly, it didn't have a chance to fall out of solution, for your sodium acetate to fall out. So here they added a crystal, a seed crystal right here. I think it was right here, or maybe it was down here. I don't know, it's hard to tell what's going on with the picture. But anyway, so your sodium, and so notice it starts to crystallize. Okay, so the seed crystal gave it a nucleation point, just gave it a spot to catch on, and so then it's going to start falling out of solution, and you start crystallizing. Okay, and then it continues to go on, and this is actually a very exothermic reaction. So we use these for hand warmers and so on and so forth. Supersaturated solutions are really uncommon. Okay, but at least naturally occurring, but they do have some practical applications. The main one of which is like hand warmers. So if you go out and buy like reusable hand warmers that you put in boiling water to get them to redissolve, most of the time they're made out of sodium acetate. Okay, and so that's it for this video. Next video we'll talk about factors that affect solubility. So we'll talk a little bit about Henry's law, so on and so forth. Let me know if you have any questions, and I'll see you on the flip side.